Have you ever looked down at a steak on your plate and really wondered, what am I actually looking at? Well, today we're going way beyond the grill. We're going to take a journey deep inside the incredible hidden architecture of muscle. Seriously, next time you see a piece of meat, a steak, a pork chop, whatever, what do you really see? I mean, beyond just, dinner. Here's the thing. You're not just looking at food. You're looking at what used to be an incredibly complex biological machine. Because at its very core, meat is muscle tissue, and its intricate, almost invisible structure determines everything, from how an animal could move to the final texture and taste on your fork. So let's start our journey with the big picture. What does the basic anatomy of a muscle look like? And to make sense of all this, we're going to use a pretty simple analogy that's going to guide us through this whole thing. Just picture a whole muscle as one of those giant, thick ropes you see on a ship. Now, that big rope is actually made up of a bunch of smaller ropes, all bundled together. And each of those smaller ropes is made of thousands of individual, tiny threads. All right, so here is our map. This diagram shows a cross-section of a skeletal muscle, and it's the perfect way to visualize that big rope idea. So let's start peeling back the layers one by one. First up, on the very, very outside, you've got the epimysium. Think of it as this tough, protective jacket of connective tissue that wraps around the entire muscle, kind of like the plastic casing on a huge electrical cable. Now, if we peek inside that epimysium, you can see all these bundles. Each one of those is a fascicle. These are the smaller ropes from our analogy. Every fascicle is just a group of muscle fibers, and it's wrapped up in its own layer of connective tissue called the perimysium. And believe it or not, we can go even smaller. If you look at each individual muscle fiber, each tiny little thread in our rope, it's surrounded by the endomysium. This is a really delicate layer that just insulates every single fiber. So you've got this incredible three-layered system that gives the whole muscle its structure and strength. Okay, now we're going to zoom in even further. Forget the bundles, forget the connective tissue. We're going deep inside a single muscle fiber all the way down to the microscopic level. And the scale we're talking about here is just wild. Each muscle fiber is actually a single, super long thread-like cell. We're talking thinner than a human hair, but it could be centimeters long. It's kind of amazing. And right here, this is where all the action happens. This image shows the junction where a nerve connects to the muscle fiber. It's the command center. And inside that fiber, well, that's where we find the real engines of movement. And those engines are called myofibrils. You can see them represented down here. These tiny, tiny contractile threads are just packed inside every muscle fiber. They are the true powerhouses, the microscopic machinery that's behind every single movement an animal makes. Okay, so we've seen the incredible structure of a living, working muscle. But what happens at that moment when the muscle becomes meat? This is where a really dramatic post-mortem transformation kicks into gear. So after slaughter, this fascinating and completely irreversible chemical cascade just takes off. First, bleeding cuts off all the oxygen. The muscle freaks out and switches to this backup energy plan, but that creates lactic acid. Now, there's no blood flow to carry that acid away, so it just builds up, and the muscle's pH starts to plummet. And finally, the muscle's main energy source, a molecule called ATP, just completely runs out. And when there's no more ATP, everything just locks up. And that final step? Well, that's what leads to rigor mortis, that famous stiffening of muscles after death. What's happening is that without ATP to unlock everything, permanent little cross bridges form between the proteins inside those myofibrils we just talked about. The muscle literally locks itself into a rigid, stiff state. So we've gone from the big picture all the way down to the molecular level. Now, let's zoom back out and connect all this science to what really matters when you're hungry, the quality of the meat on your plate. So the big question is, how does all of this microscopic drama, the dropping pH, the disappearing ATP, the locking fibers, how does that actually affect how tender and juicy your dinner is? A huge part of the answer, and this might surprise you, comes down to one critical factor: stress. Specifically, the stress an animal experiences before slaughter. Things like being moved around or being scared cause the animal to burn through its muscles' energy reserves, the very same reserves it needs for that really important pH drop after death. And this can lead to two very different and pretty undesirable outcomes. On one side, if an animal has acute, short-term stress right before slaughter, you can get what's called PSE meat, pale, soft, and exudative. The pH drops way too fast, the proteins get damaged, and you're left with a watery, pale piece of meat. On the other side, if an animal has been under long-term chronic stress, you can end up with DFD meat, dark, firm, and dry. In this case, there wasn't enough energy left to lower the pH much at all, so you get this really dark, tough, and dry piece of meat. But it's not all bad news after rigor mortis sets in, because over time, a process we call aging or conditioning begins. The muscle's own natural enzymes actually start to gently break down the locked-up structure of those myofibrils. This is what tenderizes the meat and develops all that amazing flavor. It's exactly why an aged steak is so fantastic. So what's the big takeaway from all of this? Well, from the most intricate little fibers all the way to the final flavor on your fork, that underlying structure is, well, it's everything. It really dictates how a muscle works in life and how it's going to taste as meat. We've journeyed deep inside the raw structure of muscle, and we've seen how it transforms into meat. But this, of course, just raises another fascinating question, doesn't it? How do fire and heat transform it all over again when we finally cook it?